Hello students and welcome you all aspiring engineers in my YouTube channel presented by Professor Priya Shimpi. In this session, we are going to study half-wave rectifier. These are the content under Unit 1. The name of the Unit 1 is Introduction to Electronics, and here is 8th point, rectifiers we have to study. In this video, we are going to study about the definition of rectifier, the types of rectifiers, the block diagram of half-wave rectifier circuit, its circuit diagram and explanation, and the waveform. Let's not waste the time. First, we will try to understand what is meant by rectifier. The process of converting AC signal into pulsating DC is called a rectification. The process of converting AC into pulsating DC, the process we called as rectification, and yes, the electronic component which does this rectification is called as a rectifier. We have to see in this video how the PN junction diode acts as a rectifier. So simply, rectifier is nothing but your diode when connected to AC supply. Let us see the simple block diagram of rectifier. At the input of rectifier, we are always going to apply the AC signals. We know that AC signals are the signals whose magnitude is continuously changing with respect to time. When such AC signals are applied to rectifier, the rectifier gives you these kind of waveforms. These kind of the waveforms. In the first diagram, you can see only the half cycles are seen. You cannot see the negative cycles. In the second case, if you see, we are seeing only the positive cycles, right? So such waveform is half cycle and these are the full cycles. So depending upon what waveform you are getting at the output, the rectifiers are classified as half wave rectifier, only the half waves are getting, and full wave rectifier. And the third one is bridge rectifier. Bridge rectifier also, the bridge rectifier also is a type of a full wave rectification. So what is the difference between a full wave rectifier and a bridge rectifier? I'll explain you in my next videos. So let us see the block diagram of half wave rectifier. Right? Half wave rectifier, it is a rectifier which applied AC signal. When applied AC signal, it gives you only the positive half cycles. That means it gives you the pulsating DC in such a way that only positive cycles are present, no negative cycle. Right? Now we have to understand why this half wave rectifier is giving you only the positive cycles and not the negative cycles. So this is the circuit diagram of half wave rectifier. What is there inside of the block? Inside of the block, if you see the circuit, you get a step down transformer. Through this step down transformer, you are going to connect AC supply to the PN junction diode. What is meant by step down transformer? You can go through my videos. You can find the explanation of step down transformer. And if you see the circuit diagram of a half wave rectifier circuit, it consists of a step down transformer, only one diode, and here I have drawn the bulb. You can write in the books, it is written as RL, load resistance. Whatever the circuit you are drawing, right, instead of drawing the whole circuit, we are going to replace its replica known as load resistance. We are always connecting a ground potential in all the circuits so that we are giving a path for the current to flow from higher potential towards the lower potential. So this is how you can draw the waveforms. This is how you can draw the circuit diagram for a half wave rectifier circuit in your books. So this is a step down transformer, right? A transformer has a primary winding where we have connected our AC supply, and voltage will be induced in secondary winding. The secondary winding is connected between the points A and the points B, and to the secondary winding we have connected a diode D, and the diode is connected in series with a load resistance RL. Right? In the books we write down as RL. If you draw the bulb is also the correct. So when I apply the AC signal at the primary, so because of this diode, the output voltage we can see only the positive half cycles. We have calculated the output voltage VO across the load resistance RL. See, where we are going to observe our waveforms, where we are going to calculate the VO, it is across the load resistance RL always. Now, diode behavior with AC signal is very interesting, right? We know that AC signal is having positive cycles, right? AC signal is having positive cycles and the negative cycles, right? So the behavior of diode is very interesting. The behavior of the diode in positive cycle is different than the behavior of diode in negative cycles. Let us see. Here we have drawn the two diagrams. The first diagram, this one diagram, you can see here, right? The current has started to flow and the bulb is glowing. Right? Why the bulb is glowing? The bulb will always glow in this particular circuit when we are applying positive cycles, right? When we apply the positive cycles, right? So that means at the secondary winding, when we are applying positive cycles, between the points A and B, right, the bulb glows. As opposite in the figure number 2, when you apply negative cycles, the bulb doesn't glow. And this happens repeatedly because your AC signal, it is a periodic function. It continues to become positive and negative. It repeats itself. So that means whenever the positive cycles are there, your bulb will glow. For the negative cycles, your bulb does not glow, and this repeats. Let us see why this happens. We have to see the operation. You can see the circuit diagram, right? I am applying only the positive cycles from the duration 0 to pi. We are applying only the positive cycles with an maximum amplitude of plus Vm volts, right? So this primary, when we are applying positive half cycle at the primary, right? So the positive voltage will induce in your secondary, right? In secondary winding also, positive voltage will be induced from the duration 0 to pi with an amplitude of plus Vm, right? So that means what happens, the point A of the secondary becomes positive with respect to point B. So I say the point A of secondary is positive and the point B of secondary winding is negative. So what happens when I apply positive cycles, right? So my diode becomes forward bias. Why this happens? You can see this is the positive terminal of the diode, which is connected with the A point of secondary, and your A point of secondary is getting positive voltage, right? So the diode positive terminal gets connected with the positive of the secondary winding. That is why your diode becomes forward bias. So how to replace this circuit? I replace the circuit by, when the diode is on, we have studied in the earlier videos, when the diode is forward bias, it always behaves as a closed switch. So in the circuits, I replace by diode is on by this closed switch. And yes, when the diode will allow the current to flow, when its voltage is 0.7 volts. So that means the diode is giving you a barrier potential of 0.7 volts. So in the circuit, whenever the diode is forward biased, we will replace by a barrier potential along with a closed switch. And this is how the current flows from the secondary winding through the diode, and see, the current will be flowing through load resistance RL. I denote it by IL. And the output voltage will be developed. The polarities here, it will be positive and it will be negative downwards. This depends upon the direction of the current flowing through the resistor. So in the circuit, in a closed loop path, current starts to flow. And that is why if I connect here in parallel with RL, if I connect the bulb now glows. So did you get why the bulb was glowing in the first case? Because diode was getting forward bias and it was allowing the current to flow through it in a closed loop path. So in the positive half cycle, the developed output voltage VO will be equal to Vm minus 0.7. Vm minus 0.7, right? And the current, the expression for the maximum current, it is often called as peak current. Maximum current or the peak current. How to find it out? Right? So the general expression for current I is equal to V by R. Right? But in our circuit, we have applied a positive voltage of Vm volts. So I rewrite this formula for maximum current in half wave rectifier circuit. Im is equal to Vm divided by, let us see the circuit once, right? Because of this Vm, the maximum current Im has started to flow in a closed loop path, right? And the current is flowing through RL. Yes, the current is flowing through the secondary winding. So that means resistance is also there in your secondary winding, and that resistance I denoted by RS, right? And the current is flowing through the diode. That means there is a resistance in the diode when it is forward bias. I denoted by RS. So in this circuit, the current is flowing through three resistances: secondary winding resistance plus resistance in the forward bias diode and plus load resistance RL. And that is the expression for maximum current through a half wave rectifier circuit, Vm upon Rs plus Rf plus RL. Now, this was the behavior of diode in positive half cycles. Now, let us see the behavior of the diode when you are applying negative cycles. See, I have drawn here AC supply, a dotted one. That means I have already explained this. Now we supposed to explain for negative cycles. When this primary winding, we are applying the negative cycles, right? So the corresponding negative voltage is developed in secondary windings, that means between the points A and B, right? So because of negative cycles are applied, your point A of the secondary winding becomes negative and your point B of secondary winding becomes positive. Now you have to see here is this terminal of the diode is positive terminal, and now this positive, it is connected to point A Now in negative cycles it is becoming negative. In negative cycles, your point A of the secondary winding, it is becoming negative. So now, because of this negative voltage, it is getting connected to the positive of the diode. So that is why what will happen? Very good. Now the diode becomes reverse biased. When you apply negative cycles, the diode becomes reverse bias because your point A becomes negative and B becomes positive. Now let us replace the circuit. Whenever the diode is reverse bias, it always acts as an open switch. So I have drawn the circuit for negative cycles, diode as an open switch. Right? So what will happen? No current will be flowing, and that is why in the negative cycles your output is 0. Let us see in the waveforms. These are the waveforms of a half-wave rectifier. This is the input AC waveform at secondary winding. And this is the output DC waveform of half-wave rectifier. What you can see here is when in the secondary winding it is positive half cycle from 0 to pi duration with an amplitude of plus Vm, your diode D is on, right? And you get a positive voltage, in this duration with a maximum peak of, with an output of VO is equal to Vm minus 0.7. If I talk an approximate output voltage, so VO will be approximately equal to Vm. This is the approximation. That means we have to omit this 0.7 when I talk about as approximate output voltage. Clear? And when you apply the negative cycles from the pi to 2 pi, when you apply the negative cycles, in the negative cycles, diode becomes off, right? And no current flows in the bulb. That means output is 0. And that is how we are removing the negative cycles are removed by the diode, right? And this cycle, it repeats. Again, in the circuit, we are going to apply the next positive cycle. Once again, your diode will become forward bias. It acts as a closed switch and it allows the current to flow. Now, once again, our output will be equal to Vm minus 0.7. Let us see the formulae for half-wave rectifier. The DC or the average voltage across the load resistance RL, I denote this by voltage, that means V, across the load resistance, that is L, and which type of signal I am looking, the DC. So this is VLDC is equal to Vm upon pi. Same about the current, same about the DC current at the half wave rectifier, that is ILDC. Current we always denote by I. We are calculating across load resistance, that is I suffix L, and DC we are looking, so this is ILDC is equal to Im upon pi. And the AC values are always defined by root mean square. So at the output of the half wave rectifier, the AC voltage VLRMS is equal to Vm by 2. And similarly, the RMS current through RL, it is ILRMS is equal to Im by 2. You have to memorize these formulas. How we have derived this, you can see in my next video. Based on these 4 formulas, you have the numericals for 2 marks in MCQ exam. Thank you.